the plan for today, so last time we wrapped up, or I guess before Lily's lecture, we wrapped up the 4 main modules of the class. So we've basically finished the experimentation section. So today we're going to start with the first of 3 miscellaneous lectures. I just took the top 3 from the survey that I sent out. So today is going to be on differential privacy. I hope to get to sort of some time at the end to just leave for y'all to ask questions about the project, about various approaches, things like that. I'm probably not going to get to, or I hope not to get to sort of the very end, which there were like a few last minute things on experimentation that I wanted to talk about. But if I get to that, that means y'all didn't ask enough questions today. So let's hope I don't get to that. Okay, so let's get started with introduction to privacy, but there's this like weird word in there called differential, so I'll explain what that means. And most of these slides are from Juba Ziani. He's a professor at Georgia Tech in operations research, and he does a lot of, his research is focused on differential privacy and algorithmic fairness, and so I borrowed most of the slides from him. And with that, I'll also say that I'm by no means an expert on differential privacy. I don't do any work in this area, but I'm like a consumer of this. A lot of people in in my research field work in differential privacy, and so I'm a consumer of this stuff, but I haven't actively worked on it. So ask me tough questions, and I might not know the answer. Okay. So what is differential privacy, or what is sort of privacy in general? What we're going to talk about today is this fundamental trade-off, which is often if you're at an organization, you want to share and release information for a variety of reasons, right? You might want to release it for transparency reasons, for reproducibility. You might be legally mandated to release some kind of information like the US Census. But at the same time, you don't want to leak sensitive information about individuals. So a lot of the data that you might have is, like people might not want it out in the public. And so the question is how do you release information for transparency, reproducibility, all sorts of reasons without leaking sensitive data about individuals? That's the central trade-off that we want to study today, that differential privacy tries to navigate. And so the problem is that these two things truly are a trade-off, is that, and we'll get to it in a little bit, but sort of like they mathematically conflict, is that often you really can't have both exactly, so you have to approximate one or the other, or approximate both. And these two things often sort of conflict in very subtle ways that might be hard to foresee. And the thing that I'm going to talk about today, called differential privacy, tries to formalize what this trade-off looks like and sort of how to, quote unquote, optimally navigate this trade-off. Okay, so I don't think I have to spend too much time on this slide on just, privacy is important. There's a lot of things about people that they might not want out in the public, but at the same time, you might want to sort of have like public reports about. So for example, this is a plot about, from the World Health Organization on sort of HIV testing rates and sort of care rates across the world. And then this is like credit file data that's available on the UCI machine learning repository that a lot of folks use. So I'm not going to belabor this point. Privacy is important for a variety of reasons. Okay, and so y'all might be thinking like, why is releasing, like, why is this a hard problem, right? So let's walk through probably the most naive thing you can do, and let's think about why that might be a problem. So here I have a table of a bunch of people's sort of names, date of birth. This one's conveniently missing. Gender, where we live, where each of us lives, and whether we have cancer. And and so let's say that you want to, you're someone who wants to release a database. You're a hospital and you want to release a database to help people, like do public health, like is local conditions causing cancer of some kind, right? Is some something in the water or in the air or something. And so what you want to do is you want to release like some of these columns, and of course age and gender might also influence what kind of cancer you have and whether you have cancer. And so you want to release a bunch of these columns to the public or to researchers. And so what's the naive thing to do with this data is you anonymize it. So let's say I just remove the name column. I don't release that. And maybe I just do some like unique hash ID that's like non-traceable back to the name, right? And so this seems fairly anonymized, right? Like sort of just like staring at this, you can't tell if I have cancer. Okay, so like, why is this a problem? Or is this a problem? Can folks maybe guess at whether this is a problem and why? Okay, good. Yeah, so the answer is I don't have the name, but I have date of birth, gender, and zip code. And so from that, can I get at the name? And so it turns out yes. So there's this really nice paper demonstrating this problem using census data by Latanya Sweeney in 2000. And so sort of what she identified is that a few attributes are basically enough to uniquely identify most of the so she did in the US, most of the US population. And in particular, most attributes, like sort of these attributes that are already public information. And so in particular, just by zip code, gender, and date of birth, she found that that's about enough to, she estimated that that's enough to uniquely identify 87% of the US population. And so what if I had this external information and sort of turns out this is information that you can like easily buy or just acquire about people. And so what if I had information externally about people's date of birth, gender, and zip code? Then, I could say then externally I could sort of de-anonymize this data set, right? Because my external data set has these three things and says that that belongs to Rick. And then I can join this with the data frame that the hospital released, and I learn whether Rick had cancer. And so if I just knew a mapping from names to this, oops. So if I just had an external mapping of names to these sort of three columns, I could do a join by these three columns to the data set that the hospital released and find out the private information. And this is far from theoretical. So in the last 15, 20 years, there's been a host of these attacks that have been made public. So for example, what sort of she did in the original paper is sort of in Massachusetts, it turns out that some anonymized healthcare data was released by hospitals to researchers, to help in healthcare research. And so what she did was she spent about $20 to buy a bunch of date of birth, gender, and zip code data from, I forget if this was from from the state, from the voter file, or whether she bought it from a private commercial, this is just available. It's pretty cheap. And then as a demonstration, turns out that only 6 people in Cambridge have the same birthday as the governor of Massachusetts. Only 3 were male and only 1 had the right zip code. And so from this hospital data, she uniquely identified the governor of Massachusetts medical records and sent them to his office as a demonstration of this. And sort of like this stuff keeps on happening. So for example, just like a month or 2 ago, the New York Board of Elections released sort of ranks, so we just had the mayoral election, and so there was the Democratic primary in May, and I think around then, and the Republican primary as well. And the primaries used ranked choice voting, right? So you had 5 candidates, and you could decide which of these 5 candidates you wanted to sort of the ranking across the 5 candidates. And the New York Board of Elections sort of released statistics by like a very fine area, I think by precinct, of what the rankings were. And what this Princeton election research lab found is that it turns out that there was only one voter in some of these precincts. And you could figure out who that voter was by cross-referencing it with public voter file data. And so, for example, they found out who Mayor de Blasio's son voted for. And this is just by combining what's public data. So all this was doing is combining 2 public data sets. Voter files are public, or you can acquire them from the state fairly easily. And the New York Board of Elections also just released rankings by precinct. Yeah, so that's a great question. So the question is there some standard for like, if you're about to release data, can you, like, you have to sort of do, like do a number of like these like cross-validation tests in order to like figure out how attackable it is. And so what the purpose of today's lecture is this idea called differential privacy, which means that you don't have to do that. Sort of if like, you know, sort of that approach of like trying to cross-validate with other data is almost always going to fail. And that's what the last 20 years have taught us. Where if you know, like you have some sense of what data is out there, but other people might have more sensitive data, or there might be more clever attacks that you haven't seen. And like that approach is just usually bound to fail. And so what we want, and what this idea called differential privacy gives us, is a mathematical proof that if you add noise to the data in a certain way, that there's no amount of external data that you can join with this that would help you learn new information. Okay. And so these are fun, so I'm going to talk about one last attack. This has a Cornell Tech connection. So in the recommendations module, I think I mentioned the Netflix competition, which spurred a lot of research in recommendation systems. And so what did Netflix do? Netflix announced, I think, $1 million prize for a machine learning competition if you could beat their internal recommendation system at the time. And they sort of, the goal was to try to predict user ratings from historical data, so exactly do the prediction part of recommendation systems. And Netflix provided internal anonymized data to participating teams. And you know, Netflix thought that they were clever, and so they did a lot of things to like try to ensure that this data was anonymized, right? So they took the approach that you suggested, and they tried doing things that like they were confident someone wouldn't be able to break it. And so what did they do? They didn't provide the full data. They provided small subsets. They didn't provide every column. They like reduced the number of columns they provided. They randomly deleted, or I don't know how random. It's like they had some mechanism to delete a bunch of ratings from each individual and each item. And they also like fudged the dates, right? So they didn't provide, like the analogy would be like they didn't provide exact date of birth, or they didn't provide exact, not date of birth here, but like view history and rating, like when someone watched something and at what time they watched it, they like added noise to the timestamps. And so like this seems pretty anonymous, right? Right, like this seems like how could I extract information about this? So it took about 2 weeks for, so 2 researchers, Arvind Narayanan, he's now a professor at Princeton, and Vitali, he's a professor here in computer science. So it took them about 2 weeks to break this. And so what did they demonstrate? They demonstrated that all you needed was imperfect, like very imperfect information. That if you had, for just 6 movies, approximately when they rated it, plus or minus 2 weeks, you could basically identify someone 99% of the time. And if you had just 2 ratings, so not even 6 movies, just 2 movies, and dates at like plus or minus 3 days, you can uniquely identify them almost 70% of the time. Thoughts on how they did it? Yes. Yeah, so that's on the next slide, but thoughts on, guesses on how they did it? Yes, there was. I was going to say maybe they used IMDb. Yep, so that's what they used. So they used IMDb, where, so for those of you not familiar with IMDb, IMDb has public profiles that you can put your name in and you can give ratings of movies. And sort of what was their idea? Their idea was that if you're going to rate something on IMDb, you're probably going to do it within some like close timestamp of when you actually watched it. And so if Netflix is giving you this this anonymous person watched this movie on this date, you can just look at, cross-reference that with IMDb and see what are the list of users who rated this item within like a few weeks of that date. And then if you have that for a bunch of movies, it turns out you can uniquely identify the person from IMDb. I mean, now this is only true for the subset of people who also provided ratings on IMDb, right? And so you might be thinking, like, this isn't bad because, like, sort of by definition, they provided their public ratings on IMDb, so it's not like those people don't consider it private information. But, so, oops. Sort of what's the problem? The problem is that your Netflix watch history is far bigger than what you publicly choose to reveal on IMDb, right? So if you just rate 5 movies on IMDb that you're fine with the world knowing that you watched, there might be another 100 things that you watched on Netflix that you don't really want the world to know that you watched. But if they can identify, if they can add the anonymous, if they can attach the anonymous user ID to a name, then they'll, then like people will know what are the 100 things you watched on Netflix that you don't want the world to know. And so by just doing this link, you'll learn, you can learn the private watch history on Netflix. And so someone ended up suing Netflix, sort of with the claim that their sort of the watch history revealed her sexual orientation to other people. I don't know the outcome of the lawsuit. I don't know too much details about this. I mean, but like IMDb is huge. Like a lot of sort of it's one of the bigger like public rating sites. Right, and so the same idea can be extended quite a bit, right? So there's a lot of other public review sites like Yelp and you know, for all sorts of things. And if you know, for example, if Airbnb releases some anonymized data and you can cross-reference it with public Yelp data, there's, you know, maybe you could figure out where all someone's traveled, or with location data, or all sorts of things. Okay. So what is the summary so far? Like, you know, hopefully, like so far you're thinking like, you know, the world's hopeless, like people can just like do all sorts of data joins and like no one should ever release any data ever. But okay, so what's the summary is that privacy is important, but trades off with things that we might care about that encourages the release of information. And the first idea, and so what's the general idea? The general idea that we can try to anonymize data sets or do things to the data to preserve privacy before they're released. And there's a lot of ad hoc things you can do. So you can like, you know, remove PII, personal identifiable information. You can edit some of the entries a little bit. You can delete some other entries. What the census use, so historically, what the U.S. Census did was, so the U.S. Census is legally obligated. So constitutionally, the U.S. federal government has to count every person in the United States every 10 years, and to release that information, or like a subset of the information that they collect. But actually, constitutionally, they're also mandated to protect the privacy of the individual respondents. And so historically, what the U.S. Census has done is there's a lot of places. So just like that election example showed, is that there's a lot of places with very few people. And so if you reveal, one person in this precinct believes X, Y, Z, then from external data, you might be able to find out who that person is and what they believe, or not what they believe, their like private characteristics that they told the census. And so historically, what the census has done is a lot of ad hoc things like suppressing small districts or doing what's called data swapping. So moving people from underrepresented groups from like one area to like a neighboring area to protect their privacy. And even with all these above techniques, there's a whole host of privacy failures. So as the census in this year was, or last year was trying to argue for something called differential privacy, they did an attack on themselves. They demonstrated that you could attack the 2010 census and recover sort of like uniquely identify like 60 or 70% of Americans from the US Census. And so that's even with their the historical techniques where they tried to preserve privacy. And so with a bunch of these techniques, you have clever people trying to preserve privacy, but you still end up having failures. And the most common way to attack is to use external data to extract information from the anonymized data that you otherwise didn't have. Any questions so far? Okay. And so what is the next idea? So the first idea is release sort of edited versions of the data set, where you're ad hoc, just like fudging some noise or removing entries or so on. The next idea is, what if you never release the raw data, you only release a bunch of statistics. And so you aggregate a bunch of statistics, take the means of columns or take the means where you group by some of the other columns and so on, and release a bunch of those statistics. Or maybe you just release like a deep learning model trained on that data for instead of releasing the raw text that your NLP deep learning model was released on, you just release the deep learning model itself. And so, for example, population level statistics, neural networks. And so why should this work? Is that you can maybe think that you're never releasing the raw data, right? You never at any point are releasing individual level details or features. And so the claim, maybe the naive thought, is that you can't identify any individual row in the data set because you never actually provide anyone access to row by row data. All you're providing them is like means across rows. Do people have thoughts on why this works or why this might not work? Any guesses? I'm going to need some coffee. Anyone?
I wonder if potentially using external data, if now you have extra information at the population level, if mathematically you can somehow now do a join and then use these population level metrics to then reconstruct what those figures would be from more minute data.
Okay, so the idea is potentially use external population level data to try to do some reconstruction. That's kind of the idea, but so it turns out you can use external individual level data as well.
I know for deep learning neural net models, there's papers that if you just release the weights, you can attack the model to find out the underlying data.
Okay. Yeah, and so the second the second answer is that there's papers that if you just release the deep learning weights, you can find out, what was the data used to train that large neural net model. Do you have thoughts on maybe why that's possible? That's a rough question.
Yeah.
Okay, and so why is this possible? The reason and why in general is like population level statistics also hard is because often you end up releasing so many statistics that you're basically like sort of the number of statistics you release is on the order of the number of original data sets. And so if you one way to think about it in, this is not what's happening in most of these settings, but another way to think about it is like if you do like a linear algebra transformation of like one matrix to another matrix, if like the second matrix is like as big as the original matrix, you can like find like you can just undo the transformation and find the original matrix. Or maybe another way to say it is sort of if you're releasing enough statistics, that's like identical to like statistically identical to releasing the actual data set, because all you're doing is you're doing like a lossless transformation of the data into statistics. And so sort of maybe another way to say that is for each column of the data, you have a summary statistic. And so one summary statistic, one mean of one column doesn't tell you anything. But if you have, for example, hundreds of thousands of columns in the data set, each of those things is revealing like a tiny, tiny bit about the individuals in the row. And then if you have enough of those columns, maybe you can reconstruct the individuals. Yeah, so let me, so I'll give you like a paper where someone does this. I don't I don't know like what a formal name would be, but so let's give like an example. And so what's an example? So suppose you have a DNA database and you want to tell if someone's data was used to construct that DNA database. And so like why might that be sensitive information? It's suppose a hospital released a DNA database to researchers for like people with this type of, like health, sort of like this type of disease. Then if you just can tell if someone's in the database, then you'll know whether they have that disease or not. And so, hospitals are potentially smart and they won't release just like the raw, they won't release the individual level like DNA for each individual. What they'll do is they'll take sort of each column, which is, I'm not a biologist, so I'm going to embarrass myself right now, is I think it's like SNPs or some sort of like, you can like split up the DNA into different parts. And then for each column, for each part of the DNA, just give like frequency data. Just say that, for right now, let's just think about each column as being binary. So say that 60% of 60% of the people have this column as a 1, 40% of it as a 0, and so on. So that's all the hospitals are releasing. And suppose you want to find out, like I have this person's DNA, can I figure out if they're in the database? And how can you have this DNA is, think you're like, what's 23andMe or all of these other companies that have genetic information about people. Or, you just steal someone's coffee cup and run a test. And now you want to find out if they're, in their database that they have cancer or something. And so it turns out from just that information, so just for each column and saying 60% of people in this data set have this column as a 1, 40% of 0, second column 59, 41, and doing this for hundreds of thousands of columns, it turns out you can actually find out whether an individual was in that data set. And what's the idea is it's actually very simple. So for each column, you just detect whether, so like you just calculate whether the sort of like how close, what was it? Okay. Okay, so for each column, you basically just detect how close the released information was to like the private like this like person's private information. So you basically take advantage of like if this person was in the data set, that would have altered the mean of each column very so slightly toward that person. And if you can do this for hundreds of thousands of columns, you can actually get a fairly high like probability estimate of whether this person was in the data set or not. And I'll just, link you to the paper for more details on that. And this is a problem because as people's genomic data becomes more and more public, then now suddenly you have to be careful about releasing these aggregate data sets. Like if you're a medical research company releasing aggregate data sets to help researchers. And sort of this paper actually demonstrated, sort of showed this method and demonstrated that it works to de-anonymize these data sets. Okay. And so I think this is a version of the neural net attack that we just heard. So what this paper showed is that a lot of these very large scale neural networks, especially the language ones, are basically memorizing a lot of the test set data. Or sorry, memorizing a lot of the training set data. And so because these models are essentially overfitting to the training set, what you can do is you can sort of identify you can like prime these models to spit out what you want it to spit out. And so this is actually so popular, sort of, I'm not sure if it was this paper who popularized the idea, but it's so popular that there's even an XKCD comic about it, which is, so what does this attacker do? This attacker starts out like, typing with something where like autocomplete is done by neural net, and starts by saying, long live the revolution, our next meeting will be at, and then the neural network will like fill it, will autocomplete the rest by, oh, the next meeting is at the docks at midnight and blah, blah, blah. The claim is that what this is doing is there was some other text in the data set that was private, that was someone was actually like filling out a pamphlet that was saying, long live the revolution, here's where our next meeting is. Right? And so even though that training data was never released by the person releasing the model basically just memorized it. And okay, so like there's less silly versions of this. So for example, I'm not sure if this has actually been shown, but sort of you could imagine this being extended for like literally just telling like GPT-3 or like whatever these large like language models that are released are, and just prime it with saying my social security number is, and then see if it auto-completes. And this is sort of maybe social security numbers theoretical. I'm not sure if this exact has been shown, but there's like a lot of examples on Twitter if you just like are in the right like Twitter sphere of like sort of these language completion models, like literally spitting out people's addresses, if and like addresses of people that like the people receiving the recommendation actually recognized because they were both like working on the same like semi-obscure thing. And so this is another version of the sort of this and like the previous example of like hundreds of thousands of columns might seem different at first, but they're essentially the same thing, right? So what's going on is even though you're never releasing the raw training data, what you're releasing, or the raw underlying data, you're releasing enough statistics, or in this case, your neural network is like being able to like autocomplete a whole bunch of things. and you're releasing so much of that that you're essentially releasing the training data. Okay, so hopefully at this point, y'all are even more despondent that like privacy isn't possible, that like no matter what you release, someone's going to be clever enough to like reconstruct it, and like maybe like transparency and auditability is impossible. We should just give up. But so what I'm going to talk, or the solution that I'm going to present today is like trying to navigate sort of this thing of like trying to provide guarantees that if you do this to the data set, then no matter how clever your attacker is, how much external data that they have, they can't learn any more information or much more information about each individual than they already have. So it's a guarantee on how much any possible attacker, no matter how powerful, could learn about about your data. And like that seems like, given everything, all the attacks that I just demonstrated, that seems like magical and impossible, right? Sort of the idea that no matter how clever someone is out there, like they can't break your data. But so that's sort of, but it turns out that is possible. And so, okay, so even if you, so far what we've learned is, okay, just like raw anonymization is not enough, even aggregations aren't enough. What's the natural next step? The natural next step is to either like not answer these queries exactly, so like don't give the correct statistics, or like add noise to the individuals in your data set. So like, do the anonymizations, do the aggregations, but also add noise. And then the question is that enough? So like the answer is clearly no, in the sense that we already saw an example with the Netflix data, and that they did add noise, and it wasn't enough there. But it turns out the answer can be yes, but you just have to be careful with how and how much noise you add. And it turns out there's mathematical proofs of if you add this type of noise and this amount of noise, then you you have like a certain privacy guarantee, and like where the privacy guarantee is written in terms of like how much additional information someone can learn about you. And so let's do an example. Actually, no, sorry, the example's on the next slide. Okay. And so sort of one more on this trade-off and the guarantee and sort of the philosophy behind this. So Cynthia Dwork, who she's a professor at Harvard, I want to say, I might be wrong. So she came up with this idea of differential privacy. And Aaron Roth's a professor at UPenn. They wrote a textbook about differential privacy recently. And so what do they say? They say, so what's the problem? The problem is if you give too accurate answers to too many questions. So if you give too many summary statistics, and each of those are too accurate, then that's good. That's that's the fundamental destruction of privacy. Is there's no way to give accurate answers to a bunch of questions, or accurate statistics to a bunch of columns, without destroying privacy. And so if you want to release a data set that enables you to either, like, you're releasing the raw data set anonymized, and that enables you to calculate a bunch of summary statistics, or you're releasing a bunch of summary statistics, then you need to add, depending on how much summary statistics can be calculated, you need to be adding more and more noise. And then the question is, how much noise? It turns out there's like fundamental lower bounds for like if there's this amount of noise, you definitely can attack it, or you can learn this much about this, like each individual. I'm not going to go into the math today. I'm happy to point you out, or I actually already have. I've uploaded links to like a lot of the differential privacy textbooks and notes on the class website. But what does this there's this paper from 2003 that like really lays out a lot of these like what are called reconstruction attacks and how much data you might need for these attacks. And they have essentially guarantees like this, where they say, like, suppose you have an adversary who can ask on the order of n queries. So another way to say it is, suppose you have, like, you're releasing something where you're releasing like summary statistics on n columns, and suppose they're able to obtain answers with some error, so some error alpha times n across the columns, then they can basically reconstruct the entire data set for a bunch of for all but like some users, where the number of users that you can't reconstruct it depends on the error. And sort of if you like squint and do the math real quickly, I mean faster than me, what you'll like find out is if you want to protect privacy on most of the data set against these sort of attacks, then you need noise that's at least on the order of square root of like the number of statistics you're releasing. And so each statistic should be should have noise on the order of 1 over square root of the number of statistics. And sort of like the exact math isn't necessary. I just wanted to show this theorem to show you sort of like that it turns out you can like sort of mathematically formalize like privacy notions, where if there's like a certain amount of noise, if there isn't enough noise, then there definitely exists an attack. But if there is enough noise, there's like no attack, no matter how clever your adversary is, no matter how much data that they have, that they can't find out more data about you. And so this is what a lot of computer science researchers and privacy advocates have been pushing nowadays, is for things like the US Census, instead of trying to do like these ad hoc sort of techniques where you're just like doing things that like seem good, like just like arbitrarily adding noise or arbitrarily doing data swaps or things like that, is that you should like pick an error, like pick a reconstruction error that you're fine with, and then use that to calculate how much noise you need to add, and then add exactly that much noise. So like a more like top-down approach to how much to add noise to your data set. And so like let's just give an example of like how this works, and maybe just to drive the point home. So suppose I have some original data set where I have a bunch of names, and then I have a bunch of other columns, and sort of the sensitive column, like whether I have cancer. And what you release is, so this is the sensitive column, which is sort of the has cancer column. And instead of releasing the original data set, you release a data set where you flip each entry of this column with some probability epsilon. Right? So you flip a coin, and if it's sort of heads, which happens with probability epsilon, I'll just flip that column. If not, then I won't. And so what's the idea? The idea is if epsilon is very, very small, then I can basically sort of the summary statistics I calculate are basically exactly the same, right? Like someone doesn't need to know epsilon. Someone just needs to know that epsilon is small, and they can like sort of trust that the mean of like the has cancer column is approximately what the mean should be, right? That I haven't introduced too much noise in the summary statistic. But if epsilon equals 0, then there's no privacy, right? So if I flip it with probability 0, then I've revealed in the release data set the has cancer variable for each person. But on the other hand, if epsilon equals 0, then like any mean that I calculate using this column will be exactly accurate, right? So if I take the mean of the entire column, or if I take the mean of the column grouped by like age or whatever, or geography, then I'll be exactly accurate. On the other end of the spectrum, if epsilon equals 1/2, so if I flip each column with probability 1/2, then I've learned nothing from the data. I've learned nothing from this column, right? So half of these entries are going to be no, half are going to be yes, and sort of like any mean that I calculate will just be 1/2 and will be completely inaccurate. But on the other hand, if epsilon equals 1/2, then I've perfectly preserved the privacy of each individual, right? There's nothing I can learn about each individual, but there's also nothing I can learn about the population. And so what all differential privacy is sort of, it boils down to something like this. You have a data set, you add noise of a certain kind, and you can parameterize how much noise you add, where the more noise you add, the more private you are. The less noise you add, the less the less accurate you are. I think I got that right, something like that. And what the theorems behind differential privacy tell you is like what that mapping between noise and accuracy and privacy look like. And another thing to emphasize is that how much noise to add isn't a technical choice, right? So the differential privacy sort of guarantees tell you what the mapping is from like the noise added to the accuracy loss or so on, but it doesn't tell you how much noise is good. And so for any of you following, for example, the census, so the US Census is like quite controversially using differential privacy and adding noise to a bunch of statistics. And you have a bunch of social science researchers sort of up in arms that if you add too much noise, then like a lot of the research that, there's entire fields of social science that use the census data as like a fundamental data source. And if you add too much noise, then you're like virtually like destroying entire fields of research because like, they can't get accurate answers using census data. But on the other hand, you have people saying, no, we need to take seriously the privacy provisions of the Constitution that says that the US Census can't reveal private information about individuals. And so those people the privacy advocates are arguing for a larger epsilon, and the social science researchers are arguing for a smaller epsilon. And there's no technical answer that'll say this epsilon is best. You just need to like make a policy choice of what you value more, whether you value the privacy more or whether you value the social science research. So what do you mean by swap the data? Yeah, so the question is okay, so if I just swap like two of these rows, then I maintain the aggregate statistics, but I maybe preserve privacy. So there's two issues with that. Is you're not actually maintaining the aggregate statistics, because what if I do, like what if, there's another column, which is like the state that we live in. I live in New York, Rick lives in Texas. And then what the statistic I actually care about is the group by on like cancer rates per state. And so the swap will destroy that. Or not destroy, but it'll make that noisy. But the other reason is that it's hard to know how much like swapping is enough, right? Like, do you swap every row with another row? Do you swap half the rows? Do you swap 1% or 0.5% or so on? And what differential privacy advocates sort of sort of claim is a big virtue of like this approach of adding noise is that like you have mathematical theorems that exactly give you the trade-off. That if you add this much noise, this is what you're defending against. And if you add that much noise, sort of you're defending against this other thing. Whereas like the swapping is more ad hoc, where the claim is, and so again, for those of you, I don't know how many of you, if any of you are following the census debates, but the claim from like the differential privacy researchers defending the census, defending sort of doing this for the census, is all the past censi, whatever, also used some privacy techniques, right? They did things like swapping, which you just suggested. And all of those things also added noise to social science research. but it added noise in a way that was not transparent, right? Is the census never released how much they did swapping or how exactly they did swapping and so on. With the idea being that if they release their source code, then that makes it actually easier to deconstruct. And what the differential privacy advocates are saying is, look, is like sort of like even like research was already sort of like noisy in the past because of what the census was doing, but at least now I can actually tell you what epsilon we're going to use. I can now release epsilon, and if you're like smart with your regressions, if you're smart with your social science, you can actually incorporate that into your analysis for like affecting your confidence intervals. Whereas like that's something you couldn't have done in the past. And so like I can just release everything about how I like added noise to the data set, and that doesn't harm the privacy guarantee. I mean, totally. So like, I mean, yes, like sort of no matter how small epsilon is, there's some research finding that's made impossible by this, right? So like, for example, is the number of people on Roosevelt Island who sort of identify as Asian American, is that 1,000 or 1,001, right? If I flip the race of even one person on Roosevelt Island, I can't get down to whether that number is 1,000 or 1,001, right? So I'm going to be a little bit off. And if you have some social science research that depends on that level of precision on like that small geographic space, then like, yeah, sort of there's like fundamentally you can't do anything. Any other questions or thoughts? Okay, and sort of I just wanted to have this this plot up here is the examples I've given, or this example is with like binary data that you're flipping it with some probability. It turns out you can do the same thing with continuous data. And what's interesting here is that like for those of you who've like taken enough probability or statistics classes, sort of you probably just like come to expect that like a normal distribution is just magical. That if you don't know the answer to something, if you just guess that it's normally distributed or guess that adding normal noise is the right thing to do, you're like right like 90% of the time. And I just wanted to add up here is that that is actually not what happens in differential privacy. It turns out in differential privacy with continuous data, what the type of noise you want to be add is what's called Laplacian noise. And so what this is just saying is sort of you're adding noise that is 0 with this probability, or like with this density, to -2 with this density, and so on. And it falls off sort of like the tails are heavier than a normal distribution, but it's peakier than a normal distribution. And for some mathematical reasons that I won't get into, it turns out that like this is the right type of noise to add. And maybe just like the more fundamental point here is like if you are in a setting where like you want to add noise to, so maybe that's one of the upshots or like the summary of this lecture is if you are in a situation where you're releasing data sets, like don't just like arbitrarily add noise yourself of like just like, oh, like adding normal noise or like adding a little bit of uniform noise is the right thing to do. Is like you should probably look up what like differential privacy advocates have said is like the right shape of the noise to add for your like your data type, and then add that kind of noise. You'll probably be much better off, right? Because like I wouldn't have guessed that this is the shape of the noise to add.
A lot of these papers are where it looks like it was 10 or so years ago. A lot of privacy, a lot of different data has now been like released in the past 5 or 6 years. Has there been any updates or any sort of cracks, I guess, with the differential privacy has been up to now, given like all of the data people kind of release at this point?
No, and sort of so the question is like like a lot of these differential privacy ideas, like that Dinner and Nissan paper was in 2003, and a lot of like the core algorithms were developed like 2003 to 2010, and since then there's been a lot of data sets released using differential privacy, and like how have those been cracked? And the answer is like maybe the stupid answer is like no, because like sort of we have a proof that says that they can't be cracked, right? That there exists no thing that can crack it under like these computational constraints, like anything that would crack it needs to be NP hard or blah blah blah. But I think sort of there's maybe, and this is part of what the census debate is really raging on, which is like sort of what is the right level, and what is the right level of noise to add, and sort of how much is too much or how much is not enough, right? Um, and I think this is like for example, like what I would like to see with like from like the differential privacy advocates in this census, which I think might exist. I don't want to claim doesn't exist because I haven't looked too far. Is sort of like they did a reconstruction attack in 2010 using like showing that the swapping algorithm is sort of susceptible to their attacks. Is take the amount of noise that they want to add for this census, and just like put in the same words like what does that attack look like? How much like given their choice of epsilon, how much privacy does it actually provide in the same terms? And I think that's like sort of maybe the types of attacks that get closer to like what you're thinking about, which is like not attacks to the fundamental algorithm, but attacks on the design choices people used when like adding noise, adding differential privacy. Okay. And so as a summary to differential privacy, there's like sort of what it illustrates and what it proves is that there's a fundamental limit to how much privacy you can have depending on how much noise you add. And then there's algorithms and sort of techniques that says this is the type of noise to add, this is the distribution of noise to add, such that you sort of are as like you're optimally navigating the privacy accuracy trade-off. And this is a quote I stole from Juba's slides. I think this is a quote from him. I don't know where he got this from. Is differential privacy is the only known framework that rigorously prevents such attacks and privacy violations. And sort of I've talked about it already. Is this is now like sort of adding the right type of noise is used in a bunch of places. So just like a cursory Google search, I could find that like when like Google, Apple, Microsoft, LinkedIn, a bunch of places release various types of data, they sort of say that they use various differential privacy techniques before releasing that data. And sort of course, controversially, the US Census is in the process of using it. Okay, any questions on differential privacy? Yeah, great question. So the question is like, what if you're not releasing this data set, but you're a company with a large machine learning model that's being trained on the data of millions of people, and then you get a request from the sort of under the European Union GDPR law, which is like their general privacy framework. And so what that law says is if someone requests that their data be deleted, then like the company has like X days to comply with deleting all traces of that person's data from their databases. And so the question is if like your Amazon or Google or whatever who've like trained a large speech model using everyone's data, how do you like sort of right? So like even if you delete the raw data, it's already being used, like it's already been used to train your neural network, right? And so like with that XKCD comic and the other attack I showed is that like in sort of that neural network might have memorized the data in some sense, and how do you undo doing that? So that's so that actually is a quite active field of research, exactly motivated by sort of laws like GDPR. And I'm not sure like what the formal connections are to like the differential privacy and the concepts I taught here, but there are sort of methods to sort of like all sorts of methods like can you run like a quote unquote private version of gradient descent where like as you're training these models, you're sort of like even during the training process, like as you're learning these weights, you're learning the weights in such a way such that like sort of each step that you take, each gradient step you take to learn these models, sort of you're like modifying the step such that you can never like trace back, like you can never try like memorize exactly the original data. And so yes, I know there's work in that vein, and then the claim would be that if you like actually learned your model using one of these techniques, then like once you've deleted the raw data, you actually are complying with GDPR because sort of the model has not memorized your sort of the training data. But if the interpretation is that, if like if I request Google to delete my data, then like sort of the accuracy gain they got from my data being there is like undone. Then like that's a harder thing, right? Is like because in theory, if everyone requested their data to be completed, the model should be useless. But sort of this claim with like like private gradient descent wouldn't actually do that. So yeah, that's a good question. I don't know like what the policy and like legal conclusions of that is. And like I just want to point out that this is like a real question because for those of you who saw that Facebook declared recently that they're going to delete all their face recognition data, they didn't say they're going to delete models trained on the facial recognition data. They're just going to delete the raw data. Yeah, good question. So the question is like, can you tune like so in the example I gave, I said that like each person has some, or like each cancer entry has probability epsilon of being flipped. And then maybe your claim is that, it's more sensitive if someone has cancer than doesn't have cancer. And so if you have cancer, then it's like flipped to no with probability 5 epsilon. And if you don't have cancer, it's flipped to no with probability like just epsilon. Um, and so I think there's two answers to that question. The first one, which is like another one of the insights of differential privacy, is that you really can't think about privacy in the context of a single entry or a single column. You really have to think about privacy as like a feature of the entire data set because, for example, those like the merging attacks that I said at the beginning, right, is sort of how those attacks work is I had external data in some other columns, and then that's how I did the join. And so even if I have no external data on the sensitive column, I can find things out about the sensitive column because of the other columns in the data set. And so in some sense, like the answer is no, and that you really have to think about this like global privacy budget. But then in another sense is like, I think the answer is yes, and that you can like sort of like you still have to think globally, but I think you can make these like local adjustments to how much noise you add. I just like, I don't know the literature well enough to like point you to a paper that does that.
I guess from a policy perspective, let's say you created this model and you want to get FDA approval, and the FDA wants to know if your model reasonably predicts cancer or not, and you are using the data set that's been like altered, and that they can't reasonably know if your model's good or not because like you changed the label. Like, how do you?
Yeah. Yeah, so the question is like, sometimes you care about the exact answer, like, you know, if you're having trained some model that needs to get approved by the FDA and so on. So I don't have a perfect answer, but I do know like what's been done ad hoc. So for example, so like I said, this is being used in the US Census to like adjust the counts in like each geography, right? But a core part of the census, so this is like constitutionally one of the purposes of the census, is to count the population of each state exactly to determine how many representatives that state gets in the House of Representatives. And that needs to be exact, right? You can't add noise to that. And so what the US Census did was it delivered that number exactly to Congress. So it delivered exactly how many people live in each state. And it put that as a constraint that I'm just going to have to release that data publicly without any noise. But then within that, you're saying is sort of what they're saying is like I can add noise at the sub-state level such that it still like adds up to the exact number I delivered at the state level. And so there's like tricks that you can try to do there, which is if like some things are more sensitive to being exactly right than others, then you can actually, this goes back to the previous question, which you can like certainly do adjustments to get some things exactly right and other things not. Any other thoughts on differential privacy? Okay, so we have about 5 to 7 minutes left in class, so sort of I'll just open it up to y'all for like questions that y'all might have about the course project and things. Yes. So you have what you should have, if I didn't make a mistake, is for each customer you have the price they were offered for item 1, the price they were offered for item 2, and then their decision for whether they bought neither item, item 1 or item 2. Right? Okay. Oh, I don't know how long my mic has been off, or it's red, so I don't know how long it's been low battery. So we'll see if the record. Okay. Sorry. Yeah, that's a great question. So what you want to do there is, I guess, like, so I mean, think back to like the pricing section and a little bit on the experimentation section, which is, yes, for each individual, you only have one pair of prices that you offered and their decision. But you have a bunch of other individuals who were offered different prices and also made decisions. And so, for example, if you were completely ignoring all the covariates and the user vectors, you could just exactly learn like the demand curves that we did in the pricing module. But now you can sort of, I think I talked about this in a few of the slides in the pricing module. I'll probably just like post a more explicit note in the coming days on like how I would recommend doing this as a hint. But you can sort of like learn a multi-class machine learning model that outputs they're going to buy nothing, they're going to buy item 1 or item 2. And then the inputs are like the prices for each item and sort of like the valuation, sort of like the dot product of the item and the user vector. And so if you are right, if all I had for the entire data set were just 2 prices, like one price for item 1 and one price for item 2, then it would be really hard to like think about counterfactuals, right? Like think back to experimentation, right? It's like you can't think about counterfactuals that you've never seen, but you can think about counterfactuals across individuals. So for one individual, you saw this price. For another individual, you saw other prices. No, so yeah, so you're never going to see the valuation. Sort of the data I gave you is the richest data I'm going to give you. This is like exactly the data that you saw in part in the pricing module. Actually, you have slightly richer data in the pricing module, and that you also have like the unit vector, the item and user vectors, like we had in the recommendation module. And so, yeah, so you just have to like output prices to try to maximize like revenue, like sort of like learn a demand function and then output prices to maximize revenue using this data. And so what I would recommend is like creating like a validation set, like sort of like, split the training data I gave you into, either use cross validation or do like training and validation within that. And then in the test data, I'm actually not even going to give you like sort of in the test data, all I'm going to give you, I'll do this in the next 2 days or so, is all I'm going to give you is a bunch of individuals, the covariates for every individual, and for like about half the individuals, their user vector. And then you're going to tell me their prices, and then you're going to submit a CSV of the prices that you give for each person for each item. And then I'm going to run some internal code to calculate the revenue that those prices generate. And like that's your like performance for part 1. Yes, so I know them. Yeah, I guess. Questions, how big the test set? I haven't decided yet, probably like a few thousand users. So good question. So the question is, does it matter how long it takes for your code to run? For part 1, I'm gonna ask you to submit your code, but really, I'm just gonna ask you to like submit the predictions. So it's just like give me the final answers, and it's like I don't care how long it took for you to run. This is gonna matter, and I'm still working through exactly how to do this. But for part 2, like I'm gonna need to be able to run your code. All right. For part 2, like we have this dynamic. So like part A of part 2, there's this dynamic thing where you you have some capacity and the user comes in and I give you I give you the user and then you tell me a price and that gives me the capacity for next, right? Like I have to like simulate this dynamic thing in part A of part 2. And then in part B of part 2, I'm gonna have to simulate a competition between like you and someone else. And so for part 2, I'm gonna need to be able to run your code. And so I'm still like working on the instructions on exactly. So Jean and I are working on instructions on exactly how to do that. But sort of like the summary, like relevant for you right now, is sort of make sure your code can run on Google Collaboratory using the standard packages, and that it doesn't take so it can take however long to predict, right? So what I'm going to what we're working on instructions for now, or sorry, it can take however long to train your model. So what we're working on instructions right now is like how to train a machine learning model, and then what's called pickle it to sort of like store the machine learning model in a way that I can just like load your machine learning model without having to retrain it. And then as long as it can predict very quickly, so like it can take a day to train, but as long as it can spit out predictions within like a second or something, you'll be fine. Or like half a second, or like predictions shouldn't take more than a few milliseconds, right? Yeah, so the question is So like one thing you could do, which is like connects to the pricing module, is like a multi-class for like the probability of buying each item, and that's like the right generalization of like learning the demand function that we talked about in the pricing module. What you suggested is like some regression that like tries to learn their true evaluation. And so for like thinking about whether that's a good idea, I would like you should look back to like the pricing. So I think in the introduction to the pricing module, I talked about sort of why exactly that might not be a great idea. I think that's all the time we have. So, I think that's it for today. And then happy last announcements is while y'all are walking away is Wednesday is an in-person only or online only guest lecture. I'll post the link to Zoom on EdSTEM and like today or tomorrow. All of our office hours are fairly regular. Ja has it today and Friday. I have mine Wednesday and Friday, but mine this week are going to be purely remote. Cool. Oh.